All right, so we were talking about Stokes' curl theorem last time. I want to talk a little bit about some physics applications because it's so very important for any of those of you who are majoring in either engineering or physics or even chemistry. Non-trivial amount of chemistry is, PChem, right? Physical chemistry, and how electric and magnetic fields work and this kind of thing is important in chemistry. So anyway, here we go. So first thing I want to talk about is how magnetic fields relate to current, and here's a fact that some of y'all may have seen before. And that is, if you have a wire and electric current in that wire. Current just means a flow of charged particles. Okay? So if there's a current, let's say going this way in the wire, then that is a weird thing about physics, by the way, and this is just entirely empirical. They noticed this in the lab, right? So nobody really knows why this is true. This is just the way the universe is. If the charged particles if you have a current of charged particles this way, use with your thumb, again with your right hand, the fingers of your right hand will kind of twist around that wire in the way that the magnetic field points. So this current creates a magnetic field that kind of goes around like this. It sort of circles around. You might say it curls around that wire. So this fact of physics, right? The world that we live in. This is how it gets presented in a lot of high school physics classes, and that's fine. But there's a more general version of this, and that is if you have, instead of current confined to a wire, if you just have a current, a flow of charged particles flowing around freely like this. Like a flow of a fluid. I mean, again, keep in mind, every fluid that we think of as a fluid is actually made up of a bunch of little particles. Right? Water is made of a bunch of little particles, right? Molecules. So if you have a flow of a charged fluid, that creates a magnetic field too, and it's morally the kind of very similar to the magnetic field created by a flow in a wire. It kind of goes around. Again. I'm sorry. Kind of like that. Right? And so again, if your thumb is generally in the direction that the current flow is going, right, then your fingers of your right hand will sort of curl around that in the direction that the magnetic field goes, roughly. Right? Okay, so of course, where have we seen this picture before? Right, this picture where we have an arrow and something kind of twisting around it. Right, this is a picture of curl. Right. So what we have, suitably interpreted, is that. And by the way, let me label these things in purple. Here I have the magnetic field. They use B for that, typically, and they use J for the current field. And so you can see from this picture, it would be plausible to kind of speculate, and it is also, side note, true, that the curl of the B field is the J field with a constant to be dealt with as well. So curl of the magnetic field gives you the current flow field. So true fact, this is one of Maxwell's equations. This is depending on how you count, either the third or the fourth. It's the third one I'm showing you. It's arguably the fourth in most listings. But anyway, this is one of Maxwell's equations, and just like the other Maxwell's equations that we talked about, remember last time we were talking about there was a differential version of Maxwell's equations and there was an integral version, and they're kind of the same. One's just a local version of the other being a global version. right? And they're connected by way of Gauss's divergence theorem. Well, likewise, this is a local version. You might call this the differential version of Maxwell's equations. And there is an integral version, and again, it comes about by one of the boundary theorems, this time Stokes' theorem. So this is, of course, why we're interested here in this context. If you look at this equation, if you take a flux of both sides of that equation, right? You take flux of both sides. Well, Stokes' curl theorem says that the flux of a curl is a circulation. And if you think about it, then also, furthermore, constant comes out to the right there. Nothing interesting there. What happens if you take a flux of a flow field? And think back to our very definition of flux. Flux says, interpret your vector field as a flow of fluid. And flux is the total quantity of fluid per unit time. Well, this vector field is the flow of a fluid. This J field is the flow of this fluid of charged particles. So by definition then, really, this flux of this current flow field is the total quantity per unit time of charged particles moving through the surface. And there's a word for that. It's called current. If you've had any sort of experience with electricity, you've probably heard of current. It just says how many charged particles are going at, past a point, any given point in time. So this is that other version then. We have here now the two versions of this one of Maxwell's equations. Again, I'm going to call this one equation because they're basically the same thing. They're connected so quickly. The connection between these theorems is Stokes' curl theorem. Right? So it immediately connects these equations. Okay. All right. And again, like we saw with the electric, with the divergence stuff. Here we have a quantity, and here we have its corresponding density. That's circulation. That's circulation density. Okay, oriented circulation density. Anyways, appropriately interpreted, that's the density. Okay, so strong analogies. I would encourage you to look at what we have here, compare it, flip several pages back, and look where we talked about Maxwell's equations regarding divergence of the, let's say, electric field, and notice that they're different statements, of course, right? One's about divergence, one's about curl, one's about the electric field, one's about the magnetic field. But in terms of the sort of mathematical strategic structure, right, very, very similar. Okay. All right. Then while we're here, and this one I'm going to be a little bit more quick with, but here's another empirical fact about the physical world, and it's just something you can just notice in the lab. It's hard to notice, but nevertheless it's something you can notice in the lab. And that is if you have a changing magnetic field, so this is no longer a steady state, sort of static sort of situation, but if your magnetic field is for whatever reason changing, right? The rate of change of the magnetic field is the curl of the electric field. So, again, it's just empirical. Why is the universe built this way? I don't know. Nobody knows. It just is, right? So we have empirically observed that this is true. Again, we can turn this Maxwell's equation into another version. This is the differential version of this Maxwell's equation. This is, again, typically viewed as morally kind of the same equation. This is just the integral version of it. Again, the connection is to, just like the one above, take the flux of both sides of that equation, wave the magic wand of Stokes' curl theorem, right? And then just observe, well, that's just magnetic flux. Let's just sort of write that as magnetic flux. And there you go, right? And here we have a statement about electric circulation, and here we have a statement about electric circulation density, curl. Okay, all right. Now, real quick, for those of you who are engineers or interested in engineering, this is the big idea behind how electric generators work. That's pretty neat. I think this is worth taking a moment. This idea that we can take physical motion, like I can take my arm and I can crank something and I can make it turn, or I can, rig up a steam engine or whatever, and I can make physical motion. How in the world are you going to convert that into electricity? Right? Well, roughly speaking, this equation is what does it. And the big idea is, and by the way, this is very much how it's done, okay? But let's look at the right side of this equation. This says magnetic flux, if it changes, right? Which, by the way, that's not hard to do. I can take a magnet, right? I can take a surface that has a wire wrapped around it. I can take that magnet and I can just kind of move it like this. You just physically move that magnet around. You're going to be changing the magnetic field everywhere. You're certainly going to be changing the amount of magnetic flux that goes through that surface with the wire wrapped around it. So this is the right-hand side of the equation, a changing magnetic flux. And what does that create? That creates electric circulation, electric field, that which pushes charged particles. That creates a circulation of that around the wire, and that's what pushes charged particles through the wire and makes a current, sometimes called an EMF in this context. So again, that's how electric generators work. Now there's a bunch of little details about how can you do this most efficiently and stuff like that. But they came up with this idea a very, very long time ago, and as a result of having done so, you can make a very antiquated looking item which has a hand crank on it, and you sit there and you turn the hand crank and the light bulb comes on. And that's how it works right there, that equation. So, yeah, I think that's pretty neato. By the way, electric motors work off of a similar sort of clever twist on this idea. Okay. All right. Moving along. So we're going to go on to path independence now. Path independence is a weird little topic, surprisingly important. And it comes, my foot in the door to talk about path independence is going to be look at the fundamental thermal line integrals, and of course y'all recognize the fundamental thermal line integrals. And here's the weird thing about the fundamental thermal line integrals. If I have a curve like that, right, and if I were to do a line integral over that curve of a gradient field, right, then the answer is computed as f of x1, f of the end point minus f of the starting point. Right? Old news. We know this is true. And now let's just take a pause and stand back and look at this and note that what's weird about this calculation is that two things that are computed in very different places are always equal. How weird is that? Right? That we have a calculation that's done entirely on the blue points, and another calculation that's done entirely on the green points. They're different points. They're totally different sets of points. And yet you always get the same value. That's weird. Right? Now, sort of as a free immediate consequence of that, I guess I have to zoom out one notch. Here we go. If I have two paths, C1 and C2, and look at their respective line integrals. Right, so here's two paths, C1 and C2. Well, both of these curves have the same endpoints, and therefore f of endpoint minus f of start point are the same, and therefore these two line integrals on these totally different curves are computed with the same formula from the fundamental thermal line integrals, and therefore those two line integrals themselves are the same. Right? So that's pretty wild if you think about it. And I want to take a moment to dwell on this. These are two different curves. Two totally different curves. And yet, the line integrals of a gradient field on those two totally different curves will always give you the same value. So that's weird. Right? This is unexpected, and this is certainly not true of all vector fields. This is a special property of gradient vector fields, right? Well, let me rephrase that. It is only because we know that these are gradients that we were able to make this argument about the fundamental theorem of line integrals and therefore come to the conclusion that we just did. So we currently, for the moment, only know that this property is true for gradient vector fields. Okay, so I want to write this down as a property, something that I can give a name to. If you have a vector field, we say it's path independent. That vector field is path independent. If it has this feature that whenever you have two curves that have the same starting and ending points, if their line integrals are always equal. And of course, it's very important the curves have to start and end at the same point. I mean, notice in the picture the curves start and end at the same point. The whole argument would have never flown in the first place if those curves had not started and ended at exactly the same points. Okay, right. Okay, so this is when we say path independent. Henceforth, this is what we mean. A vector field is path independent if the path doesn't matter. Starting and ending points, of course, have to matter. That's clear. Right? But if you could take any path you want between the given starting point and the given ending point, you always get the same answer for the vector field for the line integral. That shocking feature, if true, is called the path independence. Path independence of the vector field. Specifically, it's a property of the vector field. A lot of people misunderstand path independence and think, oh, the curve is path independent or something. That's not the thing, right? It's not a feature of the curve. It's not a feature of the integral. It's a feature of the integrand. It's a feature of the vector field. Okay. Again, it's the fact that these are a gradient, right? The vector field is a gradient that we were able to draw the conclusion in the first place. Okay, so what we know from our above observation is that gradients are path independent. And you'll notice how I have this drawn here. Gradients are path independent. If you have a gradient, then it follows that it's path independent. Okay. Now, the next question I want to ask is, can I go the other way? Is it true that every path independent field is a gradient? Let me say that other way, a different way. How would might there be other vector fields that are path independent? I know gradients are, yeah. What about other vector fields? Maybe there's some other vector fields which, for completely different reasons, right? They're not gradients, so we're not going to cite the fundamental theorem of line integrals, but maybe for some other reason that I haven't thought of yet, might happen to be path independent. And we don't have time to go through the argument as to why the answer to the question is what it is, but it turns out the answer to the question is there are no other such vector fields. If you have a path-independent vector field, and asterisk, I'm ignoring regularity conditions. I want to only talk about vector fields and functions that are continuous and differentiable, and everything's nice. Things get more complicated if you have irregularities, and it's just not what this class is about. Anyway, if it's path independent, it's a gradient. Okay. All right, so this is a really neat observation. These vector fields we now see are special. There are plenty of vector fields out there, right? Some of them are gradients, some of them are not. We saw this with great disappointment when we were using the fundamental theorem of line integrals. Sometimes you can't find an antigradient. There is no antigradient because your vector field is not itself a gradient of anything. So non-gradient fields exist. In fact, most vector fields are not gradients. Only the gradients have this special property. Okay. All right, real quick example. Suppose I have a vector field F, the components are P, Q, and R, and I'm going to further tell you one additional little bit of information about this vector field, and that is that the first component has a factor of Z. Now, I've told you very little information about this vector field. Just that the first component has a factor of Z. And with that given, I want to compute the line integral over this curve parameterized there. Right, now it's tempting to say, I couldn't possibly because I don't know what the vector field is. Right, let's go through our list of techniques for how to compute line integrals. One is parameterize and plug and chug. Well, I can't plug and chug because I don't know hardly anything about the vector field. Okay, fundamental thermal line integrals maybe. Maybe I look for an antigradient. Well, I can't find an antigradient if I don't know what the vector field is. Right? So it's, what's my foot in the door? Well, what I'm going to do is capitalize on one other little piece of information. I'm going to assume that it's known to be a gradient. Now, I can't use that to find a gradient, an anti-gradient, because I still don't know what the vector field actually is. But if I am allowed to assume simply that it is a gradient of something, then we're going to be able to solve this problem. And the idea is, okay, well, if it's a gradient, then it's path independent. If it's path independent, I can take this curve here and chunk it. Right? Say, I don't like that curve anymore. Look, it's all curvy and algebraically complicated. Ugh. Right? So let's just throw that curve away with the understanding that I've got to keep the starting point and I've got to keep the ending point. Okay, well, so what are the starting and ending points? I plug in t equals 0 to get your starting point. Plug in t equals 1 to get your ending point. And this curve, this mysterious curve, starts at the origin and ends at, not far away, e comma 0 comma 0. And again, as long as I keep those starting and ending points, I can chuck this curve and replace it with instead this much easier curve that has the same starting point and the same ending point. I still haven't solved the problem yet, but I've made a lot of progress. How are we doing? Is everybody on board so far? Okay, well, turns out that this is all about to end really fast as follows. Whoops, where'd it go? Yeah, here we go. So we've got this curve, and the parameterization is 0 to 1, right? And I know I have this formula back here for what x is. I can compute x prime pretty easily. It's just e comma 0 comma 0. There's my derivative. So x prime is e0, 0. These zeros make those two terms go away. Right? I'm left then with just e times z times this p of x thing. And, other piece of good news, don't forget our parameterization is this. And that means that z is 0. And my whole integral has just turned into 0. And we're done. So, path independence allows us to solve that problem. Okay. All right. Now, admittedly, that's kind of a manufactured example. But nevertheless, it shows, a use that you can make of path independence. Now, the next thing I want to talk about is why else you need to care about path independence. And this gets to a larger point about, what is math and why do we do math, right? And a lot of people fall for the pattern that they notice in high school and earlier math classes, which is that what you do in a math class is you compute stuff, right? Math questions, they start off as either words or algebra, and they end up as a number. That's the answer to a math problem, is a number. Right? That's what math is computing things. Okay, well, this is wrong. Right? This is not what math is. Math is about using ideas to understand things, to connect these ideas to those ideas, that kind of thing. Right? And it turns out that path independence is a really valuable feature along those lines. And so here's an example of I'm going to use the idea of path independence to understand some physics. Okay, so here we go. Right. Y'all know, I hope some of y'all have had an intro class in mechanics, and y'all know what potential energy is. Okay, so if you don't know what potential energy is, first thing to know is kinetic energy. Kinetic energy is if you have something that's moving fast, like when this stylus hits my hand here, it's got some velocity, and velocity gives something called kinetic energy. Kinetic energy is a way of describing how much energy is there in the fact that something's moving. Okay. When I have it lifted up to this height, we say that it has potential energy. And that when I drop it, that the potential energy of the stylus up here, now there's no kinetic energy in the stylus, it's just sitting there, it's not moving, no kinetic energy. Right? But if I were to drop it, when it hits my hand down here, just right at the moment that it's about to hit my hand, it's got kinetic energy, but less potential energy because it's lost height. Okay. The idea is that potential energy is that which allows us to talk about the conservation of energy. I do not mean this in an environmental sort of sense, right? That's how it gets used a lot. But in the physics sense of energy is never created nor destroyed. Now, in the ecological sense, it's usable energy. Yeah, absolutely. We waste a lot of usable energy. That's a separate problem. But energy itself is preserved. Up here, that energy is just in the form of potential energy. Down here, it's in the form of kinetic energy. But the energy is the same. Okay, so this is a really big idea in mechanics. If you've ever had a class in mechanics, you know how conservation of energy is a crazy, powerful computational tool that's used to answer all sorts of questions. Okay. So, I quibble now with the idea that there is such a thing as potential energy. How do we know that there is such a thing as potential energy? I just made that up for the purposes of this conversation. That there's a value that I can call potential energy that I can associate to that being at that point, and that's exactly the amount of energy that's going to be the kinetic energy when it falls and hits my hand. Well, there's a temptation to say, yeah, sure, but here's the thing. I know how much potential energy there is up here because I can just measure how much work does it take me to lift the stylus up to this point. Now, we know how to compute work. We compute work with line integrals, right? So just compute this line integral. And once you're done, once you get to here, compute the work, that's potential energy. And here's the quibble. What path do you take? Do you lift it straight up? What if, for whatever weird reason, you decide to go up in a kind of a helix pattern? Right? That's a different path. What if lifting it along this helical pattern took a different amount of effort, a different amount of work than going straight up? If they took different amounts of work, there would be no well-defined notion of potential energy. Potential energy would be work along a line integral, but can't say which line integral. They're all different. They give us different values. We don't have a definition. One of the biggest ideas of mechanics disappears, right? You can't have conservation of energy if you don't have potential energy, and you can't have potential energy until you convince me that all of these line integrals are going to give you the same value, no matter which path you take. Said differently, you can't have potential energy until you have the idea of path independence. Right? And so this is the big point. The thing that makes this all possible is that the gravitational field is path independent. Path independence is literally the concept that allows for potential energy to exist. It's the concept, therefore, that allows for conservation of energy to exist as a concept. I think that's a real eye-opener. So now, did we just compute something? No. Is there a number in a box? No. No, there's not. This is an idea that's allowed for the creation of other ideas. This is what a lot of math is really for and about. So anyway, I like to point this out. Again, it's not really a physics class, but But I think this is an important. Here I am. Important thing to understand about why path independence is important. And now, while we're on the topic of physics, real quick, gradient fields, which we know are vector fields that are path independent. Sometimes in physics classes they will call these conservative vector fields because they are vector fields with which you could associate an idea of conservation of energy. My quibble, I would prefer if they use the word conservative to associate to path-independent fields, but whatever. Path-independent and gradient, again, assuming regularity, they're the same vector fields anyway. But anyway, you're going to hear, if in your engineering classes, in your physics classes, even in your chemistry classes, depending, you're going to hear this word conservative a lot. And so you should just realize, going forward, when they say conservative, they mean that it's a vector field that is a gradient, namely it's a vector field that is path independent. So it's just a different preference of terminology. Okay. All right, likewise, that which I would prefer to call the anti-gradient, well, in the physics context, that is the potential energy. That's what potential energy is. It's the thing whose gradient is the vector. That's the thing that allows you to talk about this vector field as being path independent. So they call this also then a potential function. So in a physics context, this is what you're going to hear, because in a physics context, that's why you care about it. You care about this function because it's potential energy. Okay? In a math context, you care about it because it's the thing whose gradient is the vector field that you're interested in. So in this class, I'm going to keep using the term anti-gradient. Just keep in mind, physics classes or engineering classes, you're going to hear potential function. Okay, so you have to be prepared for how these ideas are going to manifest in these different contexts. Okay. All right, pause for questions. How are we doing? Is everybody on board? All right. Okay. Now we have to have a fun conversation here about how this relates to curl. And quick observation: it's not clear that this should have anything to do with curl. We have been talking about. I mean, pretty much we've been talking about the fundamental thermal line integrals. Aren't we talking about gradient right now? Why would curl have anything to do with this conversation? Not clear that it should. But here's a neat fact. Now, this is, again, I think also a really important idea. This gets used a tremendous amount in different... I saw this little clever construction I'm about to show you. I saw this a lot in physics classes. So anyway, here it is. So suppose you have a couple of curves, C1 and C2. That have the same starting point, right, and the same ending point. Generically, you would think, between the two of them, they make up the boundary of some surface here. And in fact, there would be a lot of surfaces, right? You could imagine between two, curves like that start at the same point, end at the same point, that, there's a surface here, but you could there's a certain amount of floppiness that you could make in that surface, right? So you could think of this picture now as relating two curves and their shared boundary points, or you can think of this picture as being about a surface and its boundary curve. So anyway, it's interesting that the picture that we drew with path independence in mind now sort of automatically brings up another different picture that's kind of one dimension higher. That's a little disturbing. Now I want to confess, it is possible that maybe the first curve is all like tangled up in a knot, and maybe the second curve is also tangled up in a knot in some way, and maybe there is, as a result of the knotting, technically no surface in between them. This is a problem in how I've presented this idea here, but I'm just going to assert, without going into ugliness, that this can be dealt with, right? And for the conclusions that I'm about to draw, it is effectively okay to ignore this situation, right? This situation can be resolved. It's not actually a problem. It's just something that has to get dealt with. And it's something that's not, that dealing is not Math 212 appropriate. Okay, so anyway, don't worry about if you're concerned about the fact that, oh, wait a minute, how do I know that such a surface exists? Not a problem. Okay, so let's write down what we know about in this situation. Notice that the boundary of C1 is the boundary of C2. They have namely the same starting and ending points. Right, in purple there. And notice as well that the boundary of S, let's see, now I want to get the sign right. Hang on a second. I want to use the same convention I did in the algebra. Yeah, so I'm going to say that this surface has a normal vector like that. And the boundary of S is C2 minus C1. Okay, so that's what we've got in our picture there. How are we doing? Is everybody on board so far? Okay. Now that minus sign bothers a lot of people. Why'd you orient that curve the wrong way, right? I mean, there's a temptation to look at this and say, this means you oriented it the wrong way, so just, quit messing up, and do it right. I mean, let's parameterize this curve that way instead, and then this becomes a plus, and aren't we all happy? And the problem is that no, we're not happy. If we do that, if I parameterize C1, or if I orient C1 the other way, then yeah, I get a plus sign here, and I feel really good right up until I notice that then this is no longer true. In fact, C1 and C2, one starts where the other ends, one ends where the other starts. Their boundaries are now, in fact, negatives of each other. Right? So, basically here, pick your negative, right? You get to decide where you want the negative to be. But there's going to be a minus sign, one way or the other, in one of these equations. You cannot get rid of this minus sign. And the way I like to say this, the point here, the revelation is that this minus sign is intrinsic to how geometry works. This isn't a screw up. This isn't I made a bad choice. That minus sign is intrinsic to space and geometry. Okay. So anyway, heads up about that. Do be careful about that minus sign. Okay. All right. So now, having observed that, let's start writing stuff down. Let's consider this surface and its boundary curve, C2 minus C1. I'm going to write down Stokes' theorem. Here it is, perfectly innocent, just writing down Stokes' theorem as it applies to that surface and its boundary curve. And then I will remind you, boundary of S is C2 minus C1. Right? So all I'm doing here is just rewriting that boundary line integral as, well, C2 minus C1. Right? And now we're going to look at this equation, and we're going to make some smart alecky observations that are kind of cool. So here we go. First, let's consider what would happen if this were zero. Right? We're just thinking out loud here. What would happen if the curl of this vector field were zero? Well, if the curl were zero, that flux on the left side would be zero. No matter what surface you pick. No matter what curves that start and end at the same point and thus give you a surface. Any such situation, if the curl is zero, that flux is zero. Well, if the left side of the equation is zero, then it follows that the right side of the equation is zero, which means that this difference is zero, which means that these two line integrals on C1 and C2 are always the same. In other words, it would mean that this vector field here is path independent. Right? I mean, that's just how, that immediate consequence, right? If the left integrand is zero, the right side is being as it is a difference, those two things that are in the difference, they always are the same. That's what path independence is. So, this is just a beautiful little setup. But Stokes' theorem, let's see here, yeah. Stokes' theorem applied to this particular little scenario that we made shows that when the curl is 0, the vector field is path independent. We doing good? And the argument works backwards just fine, right? Same thing. If the vector field's path independent, then these two integrals are the same, which means that this difference is 0, which means this right side of the equation is 0, which means this left side of the equation is 0. No, wait a second. Hang on, slow down. You're telling me that we've got a flux integral, and no matter what surface you pick, you always get 0. Well, there's only one possibility, and that is the integrand must be 0. So path independent means that the curl is 0. Yeah?
Just for clarification.
Yeah.
So in this case, we're relating a surface integral or flux on the left side to a line integral on the right side?
Yep. That's what Stokes' curl theorem says. So Stokes' curl theorem says that a flux of curl is a line integral of the original vector field around the, now notice, around the boundary curve, right? But yeah, totally. Yep. So this is new information, right? I mean, we certainly did not have any hint of that when we were talking about path independence originally, right? We had drawn this picture, but we made the observation that gradients have this feature of path independence, but gradients, fundamental thermal line integrals, who said anything about curl? And yet, here it is, right? Path independence means that the curl is 0. So I'm gonna sort of append our list of conclusions here. We showed, most of anyway, we showed that being a gradient means path independent and vice versa. And now we have that path independent means that the curl is 0 and vice versa. So what we actually have then are 3 simultaneous conditions. And it's weird when this happens, but these conditions, from an algebraic point of view, they look totally different. This is something about taking various derivatives. This is something about computing what happens when you compute integrals, right? And this is something about a completely different kind of derivatives. You might say that this is about viewing the vector field as a derivative, and this is something about taking a derivative of the vector field. Right. So algebraically completely different, but they're all 3 conditions simultaneous. And again, now we're assuming, I don't want to get into the weeds of regularity and what if there's a discontinuity somewhere? The things do get weird, and these conclusions are not all true if you have regularity problems, right? But we're not going to go there. Okay, and so now just for terminological summary, and again, you're going to see all these terms in various places. But so here the term is gradient. This is what it means to be a gradient field. And side note, it's also sometimes called conservative. Again, a physics thing. And then, of course, there's this term path independent. And those are all simultaneous. And now we have this new thing, a vector field whose curl is 0. Remember that curl says how much is your vector field to what extent is your vector field representing a fluid that's kind of got a vortex in it, some sort of a circulation happening of the fluid. That's what curl looks like, right? So if you say that the curl is 0, what we're saying is that the vector field doesn't have any of that twisting, spinning, rotating aspect to it. And so a common term for that is irrotational. So heads up, there are, now you see here 4 different words that you're going to see in different contexts, all of which mean pretty much the same vector fields. All right? Everybody on board? Questions? All right. And by the way, I mean, it's not just sort of semantical indecision. These are referring to the same vector fields, but again, they're all kind of talking about different ideas. This says that you can create a physics concept. This says that there is a function whose certain kind of derivative is the vector field. This one says something about integrals, and this one says something about the derivatives of this vector field itself. So they're all different as concepts. They're just all talking about the same vector fields. Okay. All right. So path independence, this idea here, path independence, is a big idea. Gets used a lot. Very important. It's in every multivariable calculus book. There is another entirely analogous idea that is in very few multivariable calculus books, and I don't know why. I think it's super weird. So let me show you what I'm talking about. I'm going to go back to our down to our diagram. You all remember the diagram? We've developed most of the ideas on here. By the way, let's just quick summary. We started off just taking as a given. Let's think about these objects and these evaluations, etc. And we had this idea of boundary that a bunch of arbitrary conventions that we made up. And one at a time, we found theorems that motivated operators up here. Right, there's a two-dimensional diagram, of course, also with Green's theorem. Right. But we've motivated these various different theorems and that motivate these various different operators. And so altogether, here's our diagram. And again, the big point to all this is that the patterns are strong, right? Very strong patterns. So the way, the diagram chase that is Gauss's divergence theorem, that diagram chase it's the exact same diagram chase is on here. Okay. All right. Now I want to draw the diagram chase that is path independence. I mean, how does path independence show up on this diagram? Well, path independence is a feature of certain kinds of vector fields, certain vector fields. Path independence itself means that if you have two curves that have the same boundary points, that you get the same value for the resulting line integral. Now, that's just how I'm going to represent it. I think that makes sense, right? There's where curves are. Their boundary points are over there. Check means same, right? And then you get the same line integral. Okay. Then we observed that the vector fields which are path independent are exactly those vector fields that are gradients of something. And then we observed that vector fields which are path independent, namely vector fields which are gradients, those are also vector fields whose curl is 0. So this is my little picture of what path independence looks like on the diagram. And patterns hold very strongly on the diagram. So don't you think it's worth speculating, maybe investigating a little bit the possibility that maybe something like that might be true? And let's just speculate. Best case scenario, if the pattern holds perfectly, and we haven't developed any of these ideas yet, we don't know if this is true, but let's just, fingers crossed, let's hope. The idea, I left off one thing. I got a little ahead of myself, sorry. One other thing I wanted to mention. The thing that connects these two items in the first place, the idea of path independence with the idea of being a gradient, the thing that connected those was, let's see, what color am I going to use for that? I'll use blue for that. Was the fundamental theorem of line integrals. That's what allowed us to connect these ideas. I'll use a different color. I'll use orange. This allowed us to connect that idea to that idea. Right? And then this is what allowed us to connect that idea to the green idea to the yellow idea, came by way of Stokes' curl theorem. So now let's speculate wildly. Maybe this is true. Fingers crossed, right? But could it be that there is an idea of that certain vector fields that would have the feature that whenever you have any two surfaces with the same boundary curves, that the fluxes through those two surfaces should be equal. Is that a thing? And if so, is it curl fields that have that property? Is it Stokes' curl theorem that allows us to make that connection? And can we furthermore use somehow Gauss's divergence theorem to draw some conclusion about how such vector fields must have divergence equal to 0? Is that I mean, that's what the pattern would kind of suggest in our wildest dreams. And it's all true. All true. So let's talk our way through it. So here's Stokes' curl theorem. Stokes' curl theorem says, here, let me, here's my diagram. If I have two surfaces with the same boundary curve, now, this is not boundary points, of course. These are surfaces we're talking about. We have this kind of lumpy thing, right? And there's a top surface and a bottom surface that sort of meet along their boundaries. They kind of zip up, if you will, along the boundary, right? And so the top surface and the bottom surface, they have the same boundary curve. Okay. By the way, let's be careful with orientations. If S1 is oriented like that, now I need them to have the same boundary curve. That means that the boundary curve has to have the same orientation. So we got to think now about, well, what direction then should we orient the bottom surface? And you got to play the game with, normal vectors and swirls and side swipes, and think through, well, what's the ensuing boundary on the curve, and then what has to be the ensuing orientation on the blue surface down there, and it has to be, as it turns out, that way. And it feels wrong. It feels like, well, wait a second, isn't the green one outward and the blue one inward? Isn't that kind of backwards? There's temptation to say that's backwards, but but I remind you that let's look back at this curve picture. Right, there's a temptation to say that these two curves, one of them is oriented the wrong way. Isn't this one clockwise? Isn't that sort of the right way to go? And isn't this one counterclockwise? And isn't that the wrong way to go? That's the worry about this minus sign. Right? And that's not the only perspective. What we need to make sure of is that the boundaries of these two curves are the same points. And likewise here, what we need to make sure is that the boundary of these two surfaces are the same curve. Right? So this is how the orientations have to go. Okay. All right. So given that picture, these two surfaces have the same boundary curve. And then if they have the same I got to come all the way back over here now. Here we go. These two surfaces have the same boundary curve. The green surface, the blue surface, they have the same boundary curve, and therefore their flux, the flux of a curl field through those two surfaces, those are line integrals across the same shared boundary curve, and so you're going to get the same answer. And so therefore, these two fluxes are going to be equal. Everybody on board? And notice Stokes' curl theorem, as predicted, Stokes' curl theorem has allowed us to draw the conclusion that if you're looking at a curl field, then this feature of surface independence, two surfaces with the same shared boundary curve, will have the same value of the flux. Okay, here we go. Yeah. Okay. All right, so everything's starting to line up. We've already kind of seen this part, right? And let's go back to over here. We're going to make this as a definition. By the way, again, this is a feature of the vector field. This vector field, the fact that it is a curl, the fact that it's a curl is what allows us to invoke Stokes' curl theorem in the first place and make the connection to boundaries. Okay, so this is the magic that makes this seeming coincidence work. The magic is the fact that that these are curl fields. Okay. The vector field is surface independent. Whatever this vector field is, it's surface independent if whenever you have two surfaces with the same boundary curve, that these integrals are equal. Okay, that's our definition. How are we doing? Is everybody okay? Okay. I'm such a big believer, y'all all know this, but such a big believer in thinking about this from a diagram point of view. Take the time. I cannot emphasize this enough. Such a good idea. Take the time to think about the pattern on the diagram of what we just noticed, and then go back to the section on path independence and notice, oh my gosh, yeah, it really is. It's just, what we just did over here. It's just like what we did in the previous section, just one notch over on the diagram. So that's an exercise I want you all to do on your own, but just kind of compare and contrast that the start of the section on path independence and the start of the section on surface independence, they look a lot alike. And to emphasize this, when I wrote this section on surface independence, and I'm not making this up, I took the previous section on path independence and I did this great big huge copy paste. And then I went in and I changed where it said path, and I think I did a find and replace for path to surface and gradient to curl. Right? And then I went through and I checked and I made sure there's a couple little details you got to bang out, right? But so much of the I saved myself a tremendous amount of typing by doing copy paste edit. That's how strong the pattern is. And again, partly that was laziness, but also partly that was so that the presentations will be as analogous as possible, so that it'll be easiest as possible for y'all to notice the analogies. Okay, true fact harder to prove. Not only is every curl surface independent, but only curl fields are surface independent. In other words, every surface independent field is a curl. Okay, and again, I'm not going to prove this. It's beyond the scope of this course, but true fact. Again, ignoring regularity, everything in sight that we're talking about here must be continuous and differentiable and continuously differentiable and all that as necessary. Okay. All right, so here now is an analogous example. Here's a vector field. I'm going to give you as free information that this is the curl of an unknown vector field. So notice I'm not telling you the anti-curl. That's not given. I'm just telling you there is an anti-curl. And what we're going to conclude from this, of course, is because it is a curl, it is surface independent. Okay, so we've got a vector field, and now let's see here. We have a domain. We have a upward-oriented surface S. That's the part of this elliptical paraboloid with that equation, and specifically the part that's above the xy plane. So, here we go. Yeah, here's our surface. So we have an elliptical paraboloid. Elliptical paraboloid, I want to look just at the part that's above the xy plane. Just the part that's above the xy plane. So just that part. Right now I emphasize also elliptical paraboloid. You can see it right here in this equation. That's an equal sign. That's not an inequality. Right? So this is a surface. It's a surface. It's not a solid. I am not talking about there's nothing in there. It's hollow, right? And there is nevertheless this temptation. Students fall into this trap all the time, and I think it's just you got to be more you got to be really careful and literal about your interpretations of the statement of the question. But students tend to want to look at this and say, well, there was a discussion of the XY plane, and so it must be that this must be included as part of the surface, or something like that, right? And that's just not what this says. Literal reading of the question. We're looking at the part of the elliptical paraboloid that's above the XY plane, right? So the part above the XY plane. We're not saying, and also glue the XY plane to it, right? So I hope everybody sees what we're talking about here. It's important to be careful in your interpretation of the question. And this surface is open at the bottom, right? There is no. It's just as an upside down cereal bowl. Yeah, everybody good? Okay, so there's our surface, and let's see, we're supposed to compute a flux. We are given, again, free information. We're given that this is a curl. Our vector field G here is a curl of something, and therefore I conclude that my vector field is surface independent. I don't even know what the anticurl is. I don't need to know the anticurl. Just by virtue of being a curl, I know that it's surface independent. Surface independent means that I can take this surface here and I can just chunk it. Again, I can just throw this away. I don't like that surface. It's all curvy and stuff, right? It's gonna be hard to parameterize. It's gonna be annoying. There's gonna be variables all over the place, right? So I'm allowed to, as long as I pay careful attention to the boundary curve, right, as long as I leave that boundary curve fixed, I can replace this curve with any other curve that I like. So, for example, if I were a masochist, I could pick that curve. That surface. Pick any surface that I like. I could pick that surface if I wanted to. Now, again, that would make my life harder, not easier. Let's think lazy. Right? What surface can we think of that is the easiest surface at all that has this as its boundary curve? And I suggest we pick the flat one. Nice flat surface there in the XY plane. That's got the same boundary curve as the original green surface. Right? We good? Everybody happy? Right. Now we got to think orientations. It's really easy to get this backwards. A lot of students think, okay, well, let's see, the green one here is oriented outward, and so this must be oriented outward, and that's wrong. Okay, that's not the way to think. We're not interested in how these two surfaces make up part of the boundary of the solid that's on the inside. That's just not what we're interested in. Right? What we are interested in is whether these two surfaces, I'll say it this way, we're interested in arranging that these two surfaces have the same boundary as the other. Right? So we're interested in how, what's the one-dimensional boundary of these two-dimensional surfaces, not how are these two-dimensional surfaces part of a boundary of a three-dimensional thing. It's not what we're talking about. Okay. So, let's think it through. Finger curls and swirls and side swipes and all that. This orientation on the surface that was given makes the boundary curve oriented that way. I just gotta, think about the fingers and swirls and side swipes. Now, next question, what orientation on this would induce the same orientation on that boundary curve? And you just got to play the game. Two different options. One option, let's see here. If I went like that, well, down, swirl, that's going to take me the wrong way. Right? That would take me around like that, which is wrong. So, let's try the other way. Up like that. Thumb, fingers, swirl. Side swipes, correct. All right, so this original surface oriented up has the same boundary, orientation included, has the same boundary as that surface also oriented up. Everybody's happy? Yes? Okay. Okay, and just for effect, here's that shared boundary. Okay, so again, due to surface independence, goodbye lumpy surface. Hello, nice flat convenient surface. Oh, and by the way, one of the benefits of this being flat and horizontal is that, and we know it's oriented upward, is that the normal vector is super easy to write down. 0, 0, 1. Right? No such luck here with this vector. This vector, n is going to be some complicated formula. Oh my gosh. Right? And it's, this is going to be greater than or equal to 0. Yeah, sure. And that's what upward means on the green surface. Upward does not mean 0, 0, 1 in all cases, right? So it's only 0, 0, 1 because I know that this blue surface is flat horizontal. Right. Okay, so look how the calculation then goes. We've chunked the original green surface. We've replaced it with this flat blue surface. The normal vector is easy to write down, like so. This vector field that we were given, this original vector field, there it is. But our normal vector now, being 0, 0, 1, the only part of that I actually care about is the part that doesn't get multiplied by 0. And so my question now reduces, the whole thing reduces to computing a double integral of xy over this flat surface down here. And now pick your symmetry argument. Reflecting over the y-axis, you can write down the formula for the reflection. It's not hard to show that this function does have odd symmetry over that y-axis. Or if you want to use the x-axis, totally cool, that one works too. We're in a fortunate situation of this domain is symmetric over either axis. Take your pick. Doesn't matter, right? This function, furthermore, luxury, this function is odd over, take your pick, it doesn't matter which axis. So you have choices on how to make your symmetry argument, but the answer to this question is therefore 0. Right? So powerful conclusion there. Okay. Much better than if we had taken a chapter 5 approach to this problem, we'd have to take this vector field, we'd have to parameterize that surface, and it would have worked, right? But, there'd be a much more effort involved. Okay. All right. Back to our, cheat sheet. We used Stokes' curl theorem to see how curls give us this feature of surface independence. Now, next question. Does Gauss's divergence theorem allow us to connect, the idea of surface independence, I keep hitting the wrong button, connecting the idea of surface independence to divergence being 0. Is it true that every surface independent vector field has divergence equal to 0? And is it true that if divergence is equal to 0, does that mean that we have surface independence? And again, the strong suggestion from the diagram is that we should use Gauss's divergence theorem as applied to our picture to see if that's true. So again, I'm just going to follow, the diagram is pretty much telling me to do this. Right? So, okay, as instructed, here we go. Looking at this picture again. Reminder, the boundary of S1 is equal to the boundary of S2, and that's why I oriented these things the way that we did. But now, how are these the boundary of the solid on the inside? Well, let's look at this solid on the inside here, this great big thing here, and we'll give this a name, I guess. Oh gosh, let me remind myself we called it R. Okay, so let's look at R here. Okay, and I need to recolor some of these things. This is purple. So there's my boundary curve. We have this solid on the inside, and I want to ask the question: is it true that the boundary of R is made up of S1 and S2? Well, yes, the boundary of R is made up of S1 and S2. Now, again, just for clarity, I need this to look blue because that's my blue boundary arrow. What is the boundary of R? It's tempting to say S1 plus S2, but it's not. It's S1 minus S2, right? S2 is oriented inward. Boundaries are oriented outward, right? If I say plus S2, then I've got the wrong orientation on that bottom part of the boundary. So the boundary is S1 minus S2. And again, we have this minus sign. And again, it's tempting to say, we must have made some wrong choice somewhere, somehow. And I remind you that no, it's really not wrong choice. If you were to say, I don't like that, I want to orient this downward so that this becomes a plus, then you're going to get a minus sign up there. And we can't have that, right? We need these two surfaces to have the same boundary curves. That's more important than the aesthetics of a minus sign here, right? So we can't do any of that. Right. Okay. So this minus sign, that's just a fact of geometry. This is the way space works. It's weird, but that is there. Okay. All right. So with that in mind, we have a solid and its boundary. The boundary is S1 minus S2. Let's follow our own little pattern. The pattern suggests let's use Gauss's divergence theorem. We're going to apply Gauss's divergence theorem to this picture, where a boundary of R is S1 minus S2, and that gives us this. Gauss's divergence theorem. Good old Gauss's divergence theorem, right? Just straight up, triple integral over solid of divergence is flux through the boundary surface of the original vector field. Just generic Gauss's divergence theorem. The boundary of R is S1 minus S2. We look at this resulting equation here, and we can play that same game of, and again, look at how the layout, doesn't it look familiar? It's so familiar. It's the same, morally, same argument. If the divergence is 0, that means this integral is 0. That means this integral is, this right-hand side is 0. That means the difference is 0. That means that these two integrals are the same. Divergence equals 0 gives you surface independent. Just like when the curl was 0, you got path independent. Totally analogous argument. And then likewise, if a vector field is surface independent, if these are the same, the difference is 0, the right-hand side is 0, the left-hand side is 0, that means the integrand has to be 0. This is true for all solids, so gotta be 0. And so that. Okay. All right. So let me just spike the football here. So we saw originally that curls were surface independent and vice versa. Now we see that surface independent fields have divergence equal to 0. This is algebraically just a total rip-off of what we have from the previous section. And I'm going to show you one more example and make a physics observation next time. But we're pretty close to done here. So yeah. Okay. See y'all later. Have a good day. And I have homeworks to return. I just didn't bring them today. I'm sorry. They're in my office. If you would like to get your homeworks back now, follow me up to my office. We'll hand them out back up there. Otherwise, I'll be happy to give them back tomorrow. Okay, see y'all later.